Yes.
Hey, Mike.
Okay, hold on. I can do this right.
He can show his suspenders.
Let's see the suspenders, Michael. Yeah.
Don't you like them?
I love them.
I don't know why you have to cover them up.
There you go.
No.
It has a bunch of different topics.
Yeah, no.
My name is Michael Morgan. I'm the Director of Chemistry at Cisco Bravo Medical Magnet at County USC Hospital. It is my pleasure, my enjoyment today to introduce two of the most entertaining, intellectual, and enjoying people that I've ever had to work with. Dr. Marvin Lang from the University of Wisconsin at Stevens Point is a professor of chemistry. His research interests lie in the area of electron spin resonance magnetic spectroscopy. He is very active with the American Chemical Society, a member of the Board of Directors. He is member at large for the Board of Directors, and a candidate for ACS President for the coming year. Dr. Showalter from University of Wisconsin at Stevens Point, professor of chemistry, is a very active radon chemist, radiochemist, working at the State Hygiene Lab in Madison, Wisconsin. Together with a man named Gary Schulfer, they toured the country performing for elementary school, high school, colleges, senior citizen centers, civic organizations, a show called Yes, Virginia, Learning Chemistry Can Be Fun. Let's welcome you.
It's a pleasure to be here and to be able to share with you on Space Science Day. Hey, having a good time so far?
Yes.
What'd you see this morning?
Same thing we saw.
Same thing we saw. I saw the IMAX. You saw the astronaut. Wasn't she exciting? She almost wants me to climb back into going back to college and start this thing all over again. I'd love to do what she did. This is great that you're spending the day with us. We have a lot of things that we want to show you. We have just under an hour to do it in. And these are chemical principles that hopefully you are either seeing in your classes or will see in the next couple of semesters. How many here are seniors in high school? How many are juniors in high school? How many are sophomores in high school? How many wish they were in high school? Hey, look around you, kids. A lot of these folks would like to go back. You got many opportunities. Boy, the 21st century is going to be a lot better than the 20th. And you got a lot of things to look forward to.
I think what you can realize is when you've listened this morning, you see that a lot of the things that went on in the space shuttle are certainly very chemically oriented, isn't it? Talk about the cleaning of their environment and waste removal, anything like that that's involved in there. So a lot of chemistry. We hope that we can relate some of these things as we go through, and we can see that they were, again, the offspin of some of the research or some of the development work that went on in developing the space shuttle and so on.
One of the things we thought we would start out with is a very early experiment. Today, one of the things to talk about is hands-on, and this indeed is a hands-on experience. Hands-on from a historical standpoint. Many years ago, there lived a man by the name of Ira Remsen. And the story is told that he was going to study to be a physician. And while he was waiting in the physician's office one day, probably doing the same thing you and I have to do, but he didn't have Reader's Digest to read. No, he had a little pamphlet called Chemistry. And as he was reading through this pamphlet, he came across a phrase that really didn't make too much sense to him. The phrase was nitric acid acts upon copper. Can you say that with me? Nitric acid acts upon copper. He said, you know, that didn't make any sense to me. I looked around the doctor's office, and sure enough, I saw a bottle, and the bottle had a colorless liquid sloshing around in it, and it was labeled nitric acid. So it appears then that nitric acid, to him anyway, was something like water. At least it was a liquid. Maybe it was a solution of something in water. And, you know, he dug around in his pocket, and sure enough, he found a couple of coppers. Because back in the late 1800s, the size of the coins were much larger, a good-sized chunk of copper. Be a little careful. Today, our pennies are no longer made of copper. There's zinc inside, aren't they? But if you go before 1983 with the pennies, you'll find that they are made primarily of copper. And copper is kind of reddish in color, isn't it? What color is gold?
Yellow.
Got a yellowish in color. All the rest of the metals are gold. Gold. Hey, we use that word in two different ways, don't we? But most of the other metals, in fact, I think all of the other metals are silver and luster. So copper's a little different. He says, I know what copper is. I know what nitric acid is. What he didn't know the meaning of were those other two words. What were those other two words? Acts upon. And you know, he had enough curiosity and enough common sense that he put the two together just to see what acts upon meant. Now we're going to do that for you. What we're going to do is we're going to put some nitric acid, if I can get the top off of here, some nitric acid into this round bottom flask.
Remember, our Remsen didn't do it like this.
He did it right on the tabletop. Bad news, bear. What we're going to do is we're going to do it this way. I'm going to put these two pennies inside here, and then I have a piece of equipment that's nothing more than tubing, glass stopper, a little bit of a glass elbow in here. Let's see if we can't see this. Nitric acid acting upon copper. And please notice, the same thing happened for Ira Remsen. There was a change. Chemistry is an action word, folks. It really ought to be treated as a verb, not as a noun. Now, Michael, you've got the original story there. Would you read that for us?
While reading a textbook of chemistry, I came upon the statement, nitric acid acts upon copper. I was getting tired of reading such absurd stuff, and I was determined to see what this meant. Copper was more or less familiar to me, for copper cents were then in use. I had seen a bottle marked nitric acid on a table in the doctor's office, where I was then doing time. I did not know its peculiarities, but the spirit of adventure was upon me. Having nitric acid and copper, I had only to learn what the words acts upon meant. The statement, nitric acid acts upon copper, would be something more than mere words. All was still. In the interest of knowledge, I was even willing to sacrifice one of the few copper cents then in my possession. I put one of them on the table, opened the bottle marked nitric acid, poured some of the liquid on the copper, and prepared to make an observation. But what was this wonderful thing which I beheld? The scent was already changed, and it was no small change either. A green-blue liquid foamed and fumed over the scent and over the table. The air in the neighborhood of the performance became colored, dark, suffocating. A great cloud arose. This was disagreeable. How should I stop this? I tried to get rid of the objectionable mess by picking it up and throwing it out of the window. I learned another fact. Nitric acid not only acts upon copper, but it acts upon fingers. The pain led to another unpremeditated experiment. I drew my fingers across my trousers, and another fact was discovered. Nitric acid acts upon trousers.
He pulls right in his trousers.
Taking everything into consideration, this was the most impressive experiment and relatively, probably, the most costly experiment I have ever performed. It was a revelation to me. It resulted in a desire on my part to learn more about that remarkable kind of action. Plainly, the only way to learn about it was to see its results, to experiment, to work in a laboratory.
Wow. Nitric acid not only acts on copper, it acts on fingers, it acts on pants. You're going to have to take my testimony on this one, folks. The nitric acid, when it acted on the copper, became very, very warm. This flask is warm. Very warm. So when nitric acid acts upon copper, it releases then energy, doesn't it? Is there a word for that we could use? What is it? I hear bits of be bold. Exothermic. You betcha. Why do you think we go out those exit doors? Isn't that what EX means, to go out? How about if this had gotten cold? Endothermic. So that, in other words, we learned the fourth fact. You know, there's a fifth fact. What's the fifth fact that you've learned? Nitric acid acts on copper and on fingers and everything else. But remember the brown gas that was suffocating and came out of here? We piped that brown gas over to this water. Now this water was colored with a little ammonia and phenolphthalein, the coloring coming from the phenolphthalein. What happened to the brown gas? Brown gas acted upon the water, didn't it? It changed its acid-base character. It was colored, now it's colorless, isn't it? I wonder if this is finished yet. You think there's any more we're going to be able to glean out of this particular demonstration?
Sure.
What do you think it is? Hey, this was warm. What happens to warm gases?
Well, it's not quite finished yet, is it? It's still bubbling. So it must still be reacting to bring some of that NO2 gas, the brown gas that you see coming off of there, that's in there. But once it stops, then it's no longer going to be exothermic, is it? And so this is no longer going to be hot. What's going to happen to that? It's going to cool, which takes up more room. Warm gas or hot gas? Warm gas or cold gas? Warm gas. All right, so if it cools, it's going to create a, what in here? A partial vacuum. Okay, does that give you a hint what might happen? Well, no, we can't say that. We did that one time. Some physics people really got upset with us. You can't say that it will be sucked over.
Vacuums do not do the S words.
No. What happens is it's a pressure push. This atmospheric pressure here, a reduced pressure inside, will push it over, hopefully, that's in there. Well, let's wait on that for a little bit. That's going to take a little while. So you kind of keep one eye on that if you can, and one eye here on Michael. All right?
I'm very happy to see that we have some members of the military with us today. Marv has 3 sons. 2 of them are graduates of Air Force, and 1 is a graduate of Annapolis. And I believe one of them's here somewhere today.
He hasn't come in yet, but
He hasn't come in yet. He's on his way. While they were over in the Persian Gulf last year, they collected a few little trinkets. And one of the things that they brought home for Marv was a genie in a bottle. They figured we were teachers, we might have a couple of wishes like housing, food, things like that. So they brought us this genie.
You believe that?
How do you get a genie to come out of a bottle? You rub it, okay, and after you rub it, what do you do to it?
Say the magic words.
Well, the most important thing, though,
Open it.
you got to take the top off.
You have to let the genie out of the bottle.
Say the magic words now. Chemistry, chemistry, chemistry.
A little
There goes Genie. Oh, Genie.
Yabba dabba doo.
That's kind of a lazy genie coming out of the day.
Now, one thing... Big genie, too. One thing I want to mention. During the 1800s, a lot of people made a lot of money off of very innocent people by going around and performing magic for them. Most of the magic that they were performing, it wasn't magic at all. It was simple science that any high school student can understand. This is a simple demonstration. Inside of this bottle, I have some hydrogen peroxide. Not drugstore hydrogen peroxide, not 3%, but 10 times more concentrated, 30% hydrogen peroxide. And to get it to decompose, I had to do something to encourage the reaction. I added a catalyst to it. And I did that by having this little thread hanging in the bottom. And attached to the thread was a simple Lipton tea bag. And inside of the tea bag were a few crystals of potassium iodide, a relatively common salt. When they went into the hydrogen peroxide, they encouraged the decomposition of hydrogen peroxide into something else. Now, many of you will know that the peroxide's formula is H2O2. What is that very much like? What formula? Water. What's the formula for water?
H2O.
H2O. Now, when that decomposes, there's a little something left over, something else. 2 things, really. One of them is energy. If you were to come up and touch this bottle, this is another exothermic reaction like this is. It's gotten quite warm. But there's something else. What else have we taken out of the peroxide?
Oxygen.
We've taken out some oxygen. Now, we can see our genie. Okay? Can you see water? If I put a glass of water in front of you, can you see it? Can you see water? Okay. Can you see water in all 3 of its phases?
No.
No, you cannot. Can you see it in the solid? Can we call that ice? Can we see it in the liquid? Yes. Can you see it in the vapor phase when it's a gas? So could that water have been leaving as a gas? Yes. But you saw it. Steam. Steam is water in the vapor phase, isn't it? What else is involved there? As this comes out, it collects moisture from the atmosphere. And that moisture is in a vapor phase, and it condenses into the liquid phase.
So this is really condensed water vapor?
Yeah.
That's what we saw. Now, you know, in chemistry, we're very concerned about grammar. We really are concerned about grammar. We want things grammatically correct. That sentence is not grammatically correct. What's wrong with it? It's not balanced.
I can balance it.
How can you balance it?
How did I just do that?
What do you do? Put a 3 there?
Yeah.
Then you know there is the 11th commandment.
Hold it.
What's the
Can't
matter?
I do that?
Look here. See anything happening there?
No. What is the 11th commandment? Thou shalt not change the little numbers. That you cannot do. You cannot change the little numbers. What numbers can you change?
The big
The
ones.
big ones. Those are the ones out here, right?
Yeah.
All right, let's change those. What should I do? Well, if this was a 1, why don't we make it a 2? What does that do?
Put a 2.
Well, I've got, what, 4 hydrogens?
Yeah.
And I've only got 2 over here.
Put a 2.
So put a 2 there, all right. Now how, we got 2 oxygens and, well, this is assumed to be a 1, isn't it? So there's 2 more oxygens and, hey, guess what?
Balance.
It's grammatically correct now. That's called a balanced chemical equation. And we're very concerned about that because that leads to all the laws of chemistry and of physics too, of conservation of matter, conservation of energy. Whoops, we better put that here. Didn't Michael say there was some energy release, some heat? It was an exothermic reaction. Now, would you please tell me why this one isn't working?
It's working, but it's really slow today. Usually it comes over there really fast, but
Would it leak someplace?
it's coming over there, but it's really slow.
Yeah, I can see some little dribbling here.
I don't know whether there's something in the tube or sometimes it sticks on the side.
Oh, guess what? That tube is all crudded up with stuff. Here we go. It's tried. Crudded up. Where did that come from? That's a Stevens Point, Wisconsin word. Well, let's undo the crud again. I can feel it in there.
Woo! Burp the baby.
Burp the baby.
Now it's going. Look at the water here.
Hey, look at that. It's turning blue.
Hey, Marv,
Yeah.
not to be picky,
Yes?
but where are my pennies?
I told you this is a 2-cent reaction. Hey, they don't get any better. Laugh once in a while, please. Now, if this was a siphon effect, wouldn't those 2 levels be the same? So it's not a siphoning effect, is it? No, the brown gas is acting upon the water. And notice Don has to... The 2 volumes aren't the same, are they? So eventually we're going to start slurping air, aren't we? What was that noise?
That was the slurpee that you ran out when you...
That was lunch.
Now, why is that blue? Copper ion. That's, some people tell us that it is supposed to be dissolved copper. Is it really?
No.
No, if I were to dissolve salt or dissolve water or dissolve sugar into water, I could evaporate the water and get my salt or my sugar back. I've tried evaporating this stuff. I don't get my 2 pennies back. In fact, I don't even get chunks of copper back. What do we get back?
Salt.
Ah, a salt. Which one? I thought I heard it over here. Copper what?
Nitrogen.
Copper nitrate. You get copper nitrate back. Beautiful blue crystals. Wow. Well, that's the story of Ira Remsen.
Alrighty, the color sequence that we do, I think chemistry is one of the things that sort of fascinates everyone. We can do a series of color here for you that will let you predict the color as well as tell it when to turn color. How about that? What's your favorite color?
Red. Red. Red.
Tie-dye.
Indigo. Red.
But say we make this more than one color.
I hear blue,
Chartreuse.
Red.
red.
Yellow.
How about we'll compromise and say purple?
Red.
All right. All right, let's make it turn purple. Wait, which one you got? You got. Oh, Michael, the reverse thing.
What we decided we're going to do is we're going to do all of your favorite colors in the United States of America. You betcha. Red, white, and blue. We're going to have you all stand up. Come on, right where you are. You're going to sing the national anthem. This is one of... Oh, you betcha. This is audience participation. Come on. Come on, Sanford. Lead us off here. All right, here we go. You all ready? All right, here we go. Oh,
Say, can you see by the dawn's early night? It's so bright. last gleaming,
whose broad stripes and bright stars through the perilous fight. Come on!
all around
When the twilight's last gleaming, now, in this particular reaction, what we are doing is we are making hydroxide ion, but we're delaying the formation of that hydroxide ion. All of them were the same with the exception of the indicator. Now, one of those indicators is your favorite indicator. Those of you who are especially taking chemistry. Acid-base titration, what's that favorite indicator? Phenolphthalein. The other was a cousin of phenolphthalein. The one that was colorless and then blue, you have to say that one with a lip. That's thymolphthalein. Yeah. And the middle one, the one that kind of turned cloudy, the cloudy one, that, excuse me, one cylinder, that's magnesium hydroxide. Or, I think you can purchase that, can't you, Don? How do you purchase that stuff in the grocery store?
Keep going, you're rolling.
I think you call that mom. Is that not magnesium? All right. What do we got going here, guys?
Well, let me try this again.
What's your favorite color?
Red.
Purple.
Yellow.
1, 2, 3. I agree. It shall be your favorite color. If you looked around this room, I think you'd find that most of you are wearing some shade of blue or black.
Blue.
That's what this is going to be.
Blue, black?
Now, in order for this thing to work properly, what we're going to do is we're going to ask you to help us count. We're going to be pouring the material from the front beakers into the back beakers, okay? But we're not going to do them all at once. What we're going to do is we're going to pour the first one, we're going to delay for a few moments, and we're going to pour the second one, delay for that same amount of time. So if this is going to work right, it's because you're doing it right. And we'll continue on down, do all 5 of them. Don, you're going to pour them?
I'm pouring.
Okay, we're going to help Don. We're going to count to 5, and then he's going to pour the second set. Then 5, the third set. How do you count?
1, 2, 3.
1, 2, 3.
Ah, we got people who've seen this before. It's one Mississippi or 1,000. That's what kind of a group is this? This is a chemistry demonstration. We're going to count 1 chemistry, 2 chemistry. There we go. Are you ready?
All right, when I start pouring, you start counting, huh?
Here we go.
Here we go.
1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry. All right, hold it on. We got them all in. Now, watch that first one over there. When that 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 4 chemistry, 5 chemistry, 1 chemistry.
Alfonso. That's the very famous chemical reaction called the iodine clock reaction. What it does is produce iodine. I say that's kind of iodine, I guess people say, being from Kentucky. Iodine, and it has starch in it. It doesn't happen immediately because there's something in there that takes the starch, the iodine away. So it's kind of a delayed reaction called a clock reaction, iodine clock reaction. All right, what about the favorite holiday at the end of October?
Halloween.
Halloween. What's the 2 colors of Halloween? Black. Can we do it?
Yes.
Probably. Magic. No. What will it be?
Chemistry.
All right. Let me see if I can make 2 favorite colors, but what we usually do, what does the orange color signify at Halloween? A pumpkin, doesn't it? And then what does the black color represent? The witch. All right, so we call this the witch eats the pumpkin. Okay? Let's see if we can make you a pumpkin. There's a pumpkin. Now let's see what happens with that. Whoa! The witch came along and ate that pumpkin up, huh?
Now, sometimes at Halloween we talk about pumpkins and cats. You can understand now why we want the witch to eat the pumpkin. I've never seen a black cat eat a pumpkin, have you?
Have you ever seen a witch eat a pumpkin either?
So some of the people we hang around with.
Now, for those of you that don't know, I teach in a high school. And whenever you do a demonstration for a high school student that they think is neat, they always say the same thing. Do it again. Do it again. Do it over and over and over. So what I want to do is take this Nassau clock reaction and just do it over and over and over. Get a nice orange color. Stir it. Get the nice black color. Blue. Blue.
Kind of interesting, Michael, but why don't you stop now?
Okay. Well, I want to do it again.
Oh.
Blue.
Blue.
Okay, what was the other color that you saw? Orange. Kind of a clearish orange.
Colorless.
There it is.
Orange. Black. Now. Getting a little lazy.
Yeah.
This is a great reaction. This is called an oscillating reaction. There's a lot of research interested in chemistry right now in oscillating actions because it repeats itself with time. And the human race would love to figure out the mechanism for things that cycle and repeat themselves with time. And maybe we could do something weird like stop the aging process, okay? Make ourselves be young forever. These are clock reactions.
Now, how long is that going to do that, Michael?
This will go on for about 2 or 3 minutes. Now, one other interesting thing about it, when I put my hand over it, I feel a lot of little bubbles coming up. It's foaming at the surface.
Mm-hmm. In fact, it's foaming all the way through. Just as the black color leaves, there seems to be a cleansing that is the idea of gas being evolved. And if you're timing this, if you see the first appearance of the blue color, and then see when the blue color appears again, and then see when it appears the third time, you'll find that that time period is getting shorter and shorter. So eventually, what will this do? It'll all become kind of that black color, will it not? Yeah, so the period of the reaction is getting smaller and smaller.
Now we always hear so much about bad chemicals. Have you heard that in the news? And
Yeah.
you hear people say toxic chemical as if it's one word. It's not. It's 2 words, isn't it? Do you have chemicals in your body?
Yes.
Sure.
We'd like some of your chemical, if you could, please.
We need 3
We're going
volunteers.
to ask for some donations.
We need some donations. You're going to choose today.
Okay, how about right over here, Dr. Sharma?
Hey, all right.
And how about right here? Goggles. And somebody from back here. How about in the very back
Here,
on
buddy.
the right? Yeah.
Okay. Now, what we need for you guys to come around here in the front, grab one of these flaps.
We'll let you up front.
Right here in the front.
Why don't you grab a glass?
Okay. And hold it by the neck so we can see the bottom of it. Other hand behind your back. Remember how you used to have to write on the board?
Didn't you have to learn chalk penmanship in class back in 2nd grade?
No.
You're dating yourself now.
Hey, it's fun to date yourself. You know, you go out for dinner, all kinds of things. Now, what are straws for?
Drinking.
No slurping today. You wouldn't want to slurp this stuff. Well, it wouldn't hurt you, except as Don says, you'd probably want to stay close to home. All right. So what we would like for you to do is to give us a little bit of your CO2. Would you blow into these, please?
So blow in there. Don't drink it now. Bubbles. All right, to the home audience out here. Over these 2, we have acid-base indicators. The far left, we have phenol red. Sometimes it's used in swimming pools to try to be able to tell the acidity of the swimming pool. It has in a basic solution, it has this pinkish color. If it becomes acidic, you'll see what happens in the color. In the middle one, we had bromothymol blue. A little bit of ammonia. Household ammonia is in there. Whoa! And this one over here, what was this in originally for Dr. Sharma? It was clear, wasn't it? Not clear and colorless. This is our bad breath test. If it stays clear and colorless, then your breath is just kissing cheek. If it tends to get a little cloudy, it says something about what you had for lunch. You didn't have mustard on that lunch, did you? Oh, look at the colors over here. Don't look at this yet. Look at the colors over here. What color was it originally? Pink. And did it go through an intermediate color? Did you see it? Usually it goes from the pinkish, and you see almost an orange color. Halfway, did you see that? Went too fast, huh? Boy, pretty strong breath. And look at this one, Marvin. I've never seen anybody turn that one yellow.
Boy, you must be an athlete.
Usually that one stops at the green color because there's quite a wide range of pH values in there to change that one. But I've never seen anybody turn that one yellow. That's fantastic. But usually it goes through the green stage and then into the yellow. And that's caused by the acidity of the carbon dioxide, non-metal oxide that causes the acidity. I don't know about this guy. We were just kidding, weren't we? Really wasn't bad breath, was it? No. What was in there was lime water, calcium hydroxide, a saturated solution of calcium hydroxide. And the carbon dioxide plus the calcium hydroxide makes calcium carbonate, limestone.
You mean right here, he made limestone?
He precipitated in front of everybody.
Why?
So what we had was the formation of an insoluble salt, calcium carbonate, so it drops out of solution, precipitates in there. Okay, well let's give these people a nice hand. Thanks for your breath is really great, I'm sure.
We got to have some fun at this game too. And we don't need to always do it at someone else's expenses. We only do it at the expense of our friends. Former friends.
Former friend. No, that's not true.
One of the common principles that we work on in chemistry is that many materials are soluble in water. And I have one of those right here. It's a white powder in this little medicine container. And I'm putting a white powder into some water. Turns out that this powder is somewhat like tartar. In fact, that's what this is called, sodium potassium tartrate. And for those of you taking chemistry, you probably realize that most sodium, most potassium salts dissolve in water. It's one of the kind of qualitative tests that we have. And most of this is already dissolved. I had about 30 grams. This thing was almost full, and I think you can see most of it has dissolved in water. There's very little of it there. In other words, it looks like water again, doesn't it? Yeah. But I said it was sodium potassium tartrate. The tartrate ion has a lot of carbon in it. Lots and lots of carbon. About 4 carbon atoms, I believe, per unit. And if you were to burn carbon materials, I think we all know that eventually we get carbon dioxide. You just saw a few moments ago, carbon dioxide isn't very soluble in water. They were blowing through the water. What I'm going to do is I'm going to make carbon dioxide out of this stuff. Instead of burning it, what I'm going to use as an oxidizing agent is hydrogen peroxide. I've poured a little hydrogen peroxide, your 30% variety, your real strong stuff, the same stuff Michael used in this one. And that should do the number. That should do the trick. That should cause this to effervesce. Kind of like plop, plop, fizz, fizz. Oh, what a relief it is when I stop talking. Isn't that amazing?
That's neat, Marv.
It really is.
Look at all the bubbles.
The thing is, this reaction is occurring, but it's occurring very slowly. Now, there are several things that we can do to speed reactions up, to get them to go faster. I think the first thing that you and I suggest to our students is...
No, my students suggest that. What's the first thing you want to do if the reaction doesn't work? You heat it up.
Pour
You put
the coals to it.
Huh?
By the way, this just came off the hot plate. I anticipated your answer. It doesn't even seem to want to go at high temperature. What's another way I can get a reaction to go?
Add a catalyst.
Sure. The catalyst today is a cobalt ion containing solution, and I put it in this itty-bitty beaker just so that you could see. I'm going to use this. I put it in this little itty-bitty beaker so that you can see I'm using very little. Oftentimes you don't need much material for a catalyst. So let me pour that in there. What should happen? Shouldn't that just stay pink? Shouldn't that just stay pink? If I put it in water, nothing's happening. But notice something is happening. Do you know? Oh my goodness. It turned color, but I see some little condensed water vapor coming off of here. Remember the condensed water vapor? In fact, I see that thing bubbling. In fact, it's getting very hot. Just so that we don't have a mess, let me put it in here, okay? Can y'all see it in there? My goodness.
Whoa!
Now you can see why I put it in there, right? I didn't want to get a mess all over the place. I told you it was going to take off on you. But if it's truly a catalyst, what ought to happen?
Get the catalyst back.
I get the catalyst back. You know, when I was in school, they said a catalyst is something that speeds up a reaction but doesn't get involved. Look at that.
It's back to pink.
You bet. Whoa, it is hot. You like that?
There's really two broad categories of catalysts, aren't there? What we call homogeneous and heterogeneous catalysts. This is a homogeneous one. It actually is in the same phase, gets in and takes part in the reaction, and then be able to be regenerated at the end. What's in your car, like the catalytic converter, is a heterogeneous catalyst, a surface that you pass the material over and causes then the various wanted reactions.
So I think it's important, again, as Don just mentioned, you've got to be able to keep the catalyst when it's all finished. Just like in your car. You don't want to put some lead in that gas because that'll poison the catalyst. That will no longer allow it to continue to function that way. Catalyst has got to be the same in the end as it was in the beginning. It may be modeled, it may be pitted if you're doing a surface catalyst, but you got to get the stuff back out again. What I learned was wrong 30 years ago. I'm dating myself again.
Let's show you a couple of new products real quick here for you. Here's one that's been on the market for a while. Maybe you haven't seen it in this sort of form. Let's see if we can get this to work for you. You notice our very expensive equipment that we
Thanks,
have.
Grandma.
Now, we took these from poor Michael's grandma, right after she did his laundry. Grandmas are great. They really are.
I just have some water here, and usually I put food coloring, but we didn't have any, so I just going to put a little of this bromothymol blue in here just to, so you can see it a little bit better from there, just to color it up, huh? So just water. In this vial here is this powder that's the new product. It's actually been on the market for a couple of years now. It's a white powder. Not very much of it.
A lot of white powders and brown vials today.
Yeah, you got to watch that, don't you, sometimes? With this one, it's about 5 grams of material. Let me, just to give you a little bit of an analogy of how this thing works, let me ask you, if you were to make Jell-O in your home, how long would it take you from the time you actually started making it to the time you could eat it? An hour? We can do it in 4 seconds. Really? Can you believe me? All right, when I start pouring it, you count the 1 chemistries again. Ready? Here we go.
1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry.
Pour it back, Don.
I wouldn't want to eat that.
That's hard as a stone, isn't it?
Well, I don't think it's hard as stone, but it's gel, hasn't it? Very quickly like that. The product is called Water Lock. It has a property of absorbing. It's a super absorber, absorbing water. It does it in a ratio of 1,000 to 1. 1 gram of this material will take up 1,000 grams of water. All right, now as a chemist, you're coming up with something like that. It has a very peculiar property. You want to make some use of that, don't you? Some good use of that. Turns out that the most popular use of it is in diapers. I know it's an ugly looking thing to think about, but you think about the diaper, there's that you have to change it so very often, don't you? By putting something of a super absorber in there, you're able to not have to change the diaper nearly as often. In fact, you know when you know how to change the diaper, when you know when the child's ready, is when they start dragging their leg. It's time to change. It's a little heavy.
All the National Football League coaches, they're starting to look now toward the draft of 2010. They want to draft young men who've worn these Ultra Pampers because they know their legs are going to be about this big. 1 diaper all day. Don and I have a good friend out here in California. Had a granddaughter. Little granddaughter's hot, living up there in Northern California. Granddaughter climbed into one of his little bathtubs. Jerry went down to pick her up. Oh, the kid that was about 30 pounds now was 70 pounds. Now watch yourself. And the big problem with these things are they use these now also in geriatric supplies. They use it in potting soils and so forth. Be careful of the dust. If you inhale the dust, that stuff gets into your lungs. And you can imagine what it does to the fine mucous membranes in your lungs. Be a little careful of the dust. Talking about new materials, here's a wire. What's the particular conference today, the theme of it?
Just Virginia.
Spin-off. Naval Ordnance, the Nickel Titanium Naval Ordnance Laboratories. This is ninth in all. It's a wire. It's a wire made from nickel titanium alloy. It was discovered at the Naval Ordnance Research Laboratories. Oh, you might want to know why do I have it in the form of the letters ICE. That's where I met Michael. Don and I were running a workshop last summer, and he came to ICE, the Institute for Chemical Education, headquartered in Madison, Wisconsin. We made the ICE form from this. Let me just destroy that.
Oh!
Hey, Marv, we sit up all night making this.
He's got a little jig where he goes around and around to make the ICE. You know, ICE, Institute for Chemical Education, I just destroyed it on him. How are we going to fix it, Mike?
I want it back.
Now, he's carrying some hot water. You can just set that hot water right on there. That's what we do. Okay, we put the water right over here. If I put this wire into the hot water, that's a new material, folks. It's called memory metal. There's a transition temperature. This is a spin-off type thing. About 30 years ago, the first time it was observed, they're looking for uses. Maybe you folks sitting here will come up with a use. But the metal remembers its shape and its transition temperature is about 50 degrees. That's why we had to use hot water. I could deform it down here room temperature, but I couldn't get it back unless I had it above 50 degrees. Then it snaps back into place. You vary the composition, you can change transition temperatures. Eyeglass frames, several different possibilities for nitinol. What are you guys setting up over there?
I think I'm going to take a little trip up.
Up? Okay. You do that, I'm going to try this one more time. I like this.
I spent most of my youth, that long ago, racing sailboats. My mother claims I spent more time in high school on and underwater than I spent in high school. She may be right. One of my favorite things was something I nicknamed blue tide. You could only see it at night, and it's when the water would turn blue on you. Now, you might think, what's the big deal? You go to the ocean, you look at the water, it's already blue, right? But you can't see that at night. Except there are lots of very small animals in the water. Their bodies excrete different chemicals, and they react with the salts that are in the waters. And you get really interesting things out of it. I have two flasks. This green one has a bunch of different salts in it and a chemical called luminol. And this is just some water with a little bit of hydrogen peroxide. Now Liz, if you turn the lights off, and if we focus our attention on this flask, that's the dramatic effect. That's going down slowly. Ooh. Ah.
Not going on your shoes there, Mike, is it?
Nope. I hope not.
Nothing worse
They're
than
new.
blowing shoes.
Now, how many of you are in for a little professional rivalry? I've got a challenge for Marv. This is a nice reaction, and this reaction will go for about 10 minutes like that. Marv, can you slow it down? Can you make it go faster?
Sitting over in here in one of this speaker that you can't see, but that I can handle a whole. It's quite cold. It's an ice water. Remember we said we're looking for spin-off. These were laboratory curiosities just a few years ago. These light sticks, chemical light sticks, you probably use them as to hang around your neck at Halloween time so people can see you. One of my sons used to dive for the Navy. Navy divers love these things for salvage operations because you can really get into it. But the problem is, if they're cold, they're not terribly bright, are they? Now, what's yours at?
This is at room temperature. It was
Is
just
there any
sitting up
difference
here
in
on
the
desk.
intensity? A little bit. Don, what do you got?
I got one that's been in here in a little hot water. I don't know how long it's been in there. Let's see if it does anything.
Wow. So, Michael, the answer to your question is yes, I can slow it down if I cool it off.
That's right. Now, I have one of these at home that I've been using for over a week. I live in a very old apartment building, and my appliances are old. And when I moved in, there was no light in the refrigerator. So I take one of these every Friday night and stick it in the freezer and use it as a refrigerator light. And it'll last for up to a week at a time. Okay? These are not something that are completely inaccessible to you. This is another space spin-off. Okay? You can buy these at Big Five sporting goods stores, okay, or Oshman's. They sell for about $2.50 a piece, and it's wonderful to keep 5 or 10 of these in a bag in case of an earthquake. Because not only will it give you 12 hours of light, and it's cheap, and they don't really go bad, okay, it produces no heat. It gives off its energy in the form of visible light, okay, and it has no open flame. So if you have a gas leak, you can use this to walk around a dark house and not worry about it exploding.
Interestingly enough, also, by tailor-making the molecules, you can get the color to change. You don't just paint the the sleeve here, you can actually change the molecular formula of the material that's inside, and you can get these things to glow not only in green, but white, blue, red, orange, yellow. And the thing that blows my mind as a chemist, believe it or not, in the infrared and also in the ultraviolet. The biggest user today of chemical light is the U.S. military as torch snell markers. Well, we got a couple of these here. How about, oh, you got the, look at, there's another colored one. Why don't we throw one of these up there? Maybe some of you would like
All right, Morgan.
Turn them all on. That was exciting, huh?
Now, for all you high school students, what's one of the first questions that you ask your chemistry teachers when you go in the first day? I always get the same question. From all my,
Request, isn't it?
it's a request from all my science students. Can we blow something up? We're going to try that for you today.
I think the key to teaching a lot of times is to sort of channel that energy into the right places, huh? So what we've done, we want to show you a small explosion. All right, want to see one?
Yes.
All
Sure.
right, just a small one. But in order for us to do it, you must tell us what 4 things we would need in order to have an explosion. Fuel. Okay, good. Heat, or
A
spark
helicopter.
source to start off. Oxygen. We got oxygen in the air. And then the most important thing. Something to blow up. A closed system, huh? So that when the reaction happens inside there, the heat and pressure push would cause that then to have some sort of release. All right, now we have a fuel. The fuel we have is methanol, methyl alcohol. All right, that's the fuel. We needed some oxygen. We have that here in the air. All right, and we needed a spark. We have this sparker. This is in physics. It's called a Tesla coil, named after a famous physicist, Dr.
Nikola Tesla.
Tesla. And what it is, a high voltage coil that's inside here will generate quite a large voltage. And what it will cause then is, as it grounds, it will spark up. Watch this. Can you see that spark?
Yes.
All right, notice I have to come very close to that metal rim in order for it to spark. And inside here is something of the order of 30 to 40,000 volts. And yet I have to bring it within an inch in order for it to spark. So again, imagine what a lightning bolt must be in order for it to travel a mile through the atmosphere, what the voltage must be inside there.
Did you see the pictures of the lightning in the IMAX film today?
Yeah.
Lots of voltage there.
All right, and here's my container. I have this little bottle that I can put this cork on and cap that up as being the container, closed system. Huh? Well, let's put them all together. I have the methanol. I'll put the methanol inside the container. Now, methanol is volatile. That means it will go from the liquid state into the gaseous state very readily. So not only inside that bottle is the liquid, but there's also methanol vapors in there as well. And oxygen with the air, this possibly is also inside there, so it's a nice mixture of the two. I'll close that up, and I want to put this spark in there, huh? That's not going to work, is it? How am I going to get the spark in there?
How'd you get that spark to jump before?
I had some kind of metal. So what I need to make me a little spark gap, huh? I come prepared. I have 2 little files. So I'll put the files through here. Now how far should I put them apart? 2.53 centimeters.
Less than an inch.
Just a little bit less than an inch, huh? So it will jump across there. If I would touch them, it would conduct right through the metal. This way, if I get them too far away, they can't jump across. All right, are you ready?
Yes.
Watch the cart.
She wants you to do it again, Don.
We do it again?
Yes.
All right, now what do we have in the bottom? Methanol, a volatile liquid, huh? And then we have to have oxygen. We have to have a spark and a bottle. All righty. And we'll put them those 2.53 centimeters apart. Put it in there.
This is the fun part of chemistry.
Let's do it again. Oh, it came apart pretty far.
2.53.
There we go.
Try the other side. Did you break it?
Is it broken?
No.
What's wrong with it? It needs more methanol, or it needs some oxygen, I hear people say. Now, we don't have time to, but this is a whole lesson if you wanted to go into class. This is the lesson on the scientific method. Because the scientific method says you must recognize the problem. The problem here is it only works once. The second part of the scientific method is a hypothesis or a guess. They come naturally. Do you hear people say, it's out of fuel, it's out of oxygen? The third part of the scientific method is to test it. I can test it and tell you that there is fuel there. There's fuel left inside there, so it can't be that. The other thing is that it might be the oxygen that's been used up. So we need to put more oxygen back in there, huh? How about that? Oh, it's carbon dioxide I'm putting in there, huh? But it really, truly, our lungs are not terribly efficient. I understand that we only process about 15% of the air we bring in. And most of it comes back out as unspent. We just can't process it that quickly. So blowing in there, I'm also blowing, as well as CO2, blowing in some oxygen. And of course, by the Bernoulli effect, I'm not putting my mouth right directly on it. It is pulling some in there as well, some of the air. And you squeeze it, bring it in. What do you think? Think enough in there?
Let me look.
See any?
Looks good.
At the pamper him. What do you think? Think we'll try it again?
Yes.
All right, that's the fourth part. The third part is actually the testing on it. Not the fourth. The third part is the testing. Let's see if we can test it and see if it'll work again. All righty. Do you think we're all ready?
Whoa! That was it?
That was it. What's the fourth part of the scientific method?
Theory.
Theory or explanation, isn't it? And now you know that indeed when this reaction happens in here, it's a combustion reaction, it uses up the oxygen. But there was excess methanol in there, so that the idea of limiting reagent, you can go into all kinds of things that's involved in that little process there.
All right, talking about spin-off. Again, that's the theme of this conference. So the technology advances. Got a spark? See the spark in here? All this is a Coleman lantern lighter. If you like to go camping, forget your matches, well, this way you can light your lantern, okay? Container. There's oxygen, obviously, in here. Now, what this container is not a baster bulb, although it looks an awful lot like it for basting the turkey. No, this is an acid filler. These are going out of style with the new batteries that we have. But the reason we choose these is the caliber is just right, instead of a cork. And I think, Michael, are you all ready to go?
I'm ready to go.
Oh,
You
I need some alcohol.
Oh, okay.
Sir? Now, remember, when you poured that in there, you couldn't get your wick wet, right?
I didn't get the wick wet.
All right. And the objective here, of course, is to flick your bic. How do you snap your fingers? Just like that? Okay. Are you ready?
I'm ready.
All right, here we go.
Whoa! Wow, you got the technique down here?
Hey, there you go. Got any more? I need some more fuel. And more ammunition. Holy smokes. See, chemists have fun. They really do. Scientists have fun. But you got to know something about the science, don't you? What are you doing there?
Love to do it.
Hey, I want that man on my team. Now, the technology advances one step further. Please notice Professor Showalter.
That's a baster ball cannon on steroids.
All right, what I put in here was methanol again, a little methyl alcohol, mineral spirits, in this big bottle. And what am I doing now? What am I trying to do now? Vaporize it, yes. I'm trying to get this vaporized, and there certainly was oxygen in there with atmospheric pressure. So I'm trying to mix the methanol with the oxygen so that we get that intimately mixed. And then what should we do? Why don't we drop a match in? Yeah. Try that? Well, it won't blow up because it will have the opening at the top, so it will release through there. But I want to get as much of that methanol as I can vaporized in there. I like this when it's in the dark, especially in a room like this. It really doesn't make a whole lot of noise, but I hope it'll last long for you. Ready?
This is a three-person operation. Okay,
All right,
Michael.
light her up. Once you get the match lit, then you can turn the lights off. All right, put the lights down. There you go.
Oh, dancing flames! Well, we're fast coming to a close to this program that Michael has invited us to come to. I had not heard of this particular Space Science Day before. I am enthralled with what's going on here in Southern California. I know that I speak for my colleague too. You folks are having a tremendous opportunity, and you've also made tremendous contributions to science and science technology throughout the United States over its long history. We've got just a couple of more demonstrations for you, and then we're going to bring it to a close. All of these have a little bit of this whiz bang boom to it. You'll notice Professor Showalter is placing there very deftly 3 corks. The corks are designed so that they will keep the Pringles can, which he has prepared, specially prepared Pringles can. On the plane coming here, we sacrificed our bodies and ate the Pringles. That's the only way this thing works.
AP Chem kids put them down.
You want me to use that? They're going to fill that little canister, that Pringles can, with hydrogen. Now, the reason they're filling it with hydrogen is that hydrogen will burn very, very clean. Hydrogen will burn very, very clean. We're going to show you how clean this hydrogen burns, because I'm going to light it. And then I'm going to let Michael tell you a little bit about
Okay, light her up. All right, now we can get the lights down again.
You'll notice a really nice flame there. That's a blue hydrogen flame. The hydrogen itself is just burning away so it leaves the can. We'll let it go for a second.
Now there's a bigger hole in the bottom. So as this is burning, it's using up the fuel, it's drawing air in from the bottom. The air has oxygen in there. Now you remember what the space shuttle was fueled by? Liquid hydrogen, liquid oxygen. Once this holds in enough oxygen to meet the ratio that is needed, 2 to 1, it will explode. All right.
Now you have to be very quiet, because you will hear the flame. You understand now why we must use rippled or wrinkled chips? This is wrinkle your chips experiment.
Now, Dr. Lang mentioned liquid hydrogen and liquid oxygen. There's one other real neat liquefied gas that we don't really have that much time to talk about today, but I just want to show you its neat effect. Okay? When water boils, does it get hot or does it get cold? Hot. So boiling must mean hot. Is that right? No? Not necessarily? This is liquid nitrogen. And we say it is boiling cold. Pick up your feet!
Go for it, Morgan.
That's boiling!
Yeah.
Turn around, is it all there?
It's there. Small.
That's boiling cold. That has a boiling point of minus 196 degrees Celsius, minus 321 degrees Fahrenheit.
Hey, Don, if that's boiling cold, does it mean it's freezing hot?
Yes. We're too conditioned by water, aren't we? You know, boiling water is very hot, and freezing water is very cold. That's not true with most other things. Well, we got one more. This is it. What's in this balloon? Helium. You know it's helium, don't you? Indeed, you're right, but I'll tell you, those other 2 balloons don't have helium. Let me show you. We're going to ignite what's in these balloons. And by the difference in the sound of the balloons, you'll be able to tell that there's not the same gas in each one. Now, helium is an inert gas. If we bring that chart up, you'd see that, or that screen up, there's a chart underneath there for the periodic table. You'd see it's an inert gas. All right, so it
What's
won't
in
do
this
nothing.
balloon? Chemistry is a gas at the University of Wisconsin in Stevens Point.
All right. You don't have to hold your ears, it won't be loud.
Fire extinguisher.
Right? Helium gas doesn't do anything. All right, this one is not helium. This is the gas that was in the Hindenburg, 1937. The reason they put it in there was it has twice the lifting power. It's half the mass. But it has a problem. Don't hold your ears. It's a beautiful sound. I won't hurt you. I'll promise to tell you when it's loud.
Do it again! Do it again!
Now, the only reason you heard any sound was because of the oxygen in the air reacting with the surface of the hydrogen bulb that was in there that pulled out. This one, we intimately mix hydrogen and oxygen in there.
Now, some people ask us, why do we do balloons? What benefit other than the theatrics? I want you to be very careful. I want you to consider what's going on when you try to charge up a battery in a garage or in a closed area. You have the potential for generating hydrogen in a closed system, and there is oxygen there, and this is what could happen.
This is very loud. It would be like a shotgun going off in here. So we want you to hold your ears. Now, don't put your fingers in your ears. You're liable to touch your fingers. Do it like this. Sit up straight, though. We want you, because you're going to feel this on your chest.
Oh, God.
Are you ready?
Hey! Yeah, that was intense. Cool, huh? These guys are pretty right on. All right, what's next?